So, good
Good
evening,
evening,
everyone.
everyone.
This is
This is
our
our
first
first
TA
TA
session
session
for
for
Algebra 1,
Algebra-I,
that
that
is
is
your
your
NPTEL
NPTEL
course,
course,
Algebra 1.
Algebra-I,
And
and
today
today
we will
we'll
be
be
discussing
discussing
about
about
week
week
1
one
lecture
lecture
materials
materials
that
that
are
are
group
group
axiom,
axiom,
permutation,
permutation,
order
order
conjugation,
conjugation
subgroups.
subgroups.
So,
So
uh,
uh,
basically, we
basically
will be
we'll be
doing
doing
some
some
exercise
exercise
problems
problems
related
related
to
to
first day,
hashtag
first
first
chapter,
chapter,
that
that
is
is
topics in
topics
group
in group
theory.
theory.
So I
So I
thought
thought
not
not
first,
first,
second
second
chapter,
chapter.
and I
And I
think
think
there
there
are
are
several
several
good
good
exercises
exercises
that we
that we
can
can
practice
practice
to
to
start with
start with
this
this
group
group
theory.
theory.
Okay,
Okay,
so
so
we'll
we'll
start
start
with
with
our
our
problem
problem
one.
one.
So
So
yeah,
yeah,
first
first
let me
let me
write
write
this.
this.
So
So
as
as
you have
you have
just
just
learned how
learned
to
how to
define a
define a
group,
group,
we'll be
we'll be
checking
checking
if
if
some
some
given
given
objects
objects
like a
like a
set
set
if, and
and
with
with
a
a
given
given
operation
operation,
if they
if
are
they are
groups or
groups or
not.
not.
So
So
in
in
the
the
following,
following,
determine
determine
whether
whether
the
the
systems
systems
described
described
are groups
groups
or
or
not.
not.
Uh,
Uh,
Moreover,
Moreover,
if
if
they are
they are
not,
not,
point
point
out
out
which
which
of
of
the
them
group
group axioms
axioms fail
fail
to
to
hold.
hold.
So
So
let us
let us
start
start
with
with
Z
Z
equals
equals
to
to
set
set
of
of
all
all
integers,
integers,
that
that
is
is
Z,
it,
with
with
operation
operation
should
should
be
be
defined
defined
as
as
A
A
minus
minus
B.
B.
So
So
basically
basically
we
we
have a
have a
set
set
of
of
all
all
integers
integers
and
and
we are
we are
given
given
operation
operation
that
that
is
is
for
for
A
A
and
and
B
B
from
from
G.
G.
The
The
operation
operation
is
is
their
their
subtraction.
subtraction.
So
So
you
you
have to
have to
check
check
if
if
uh, they
they
form a
form a
group
group
or
or
not.
not.
So next
Next,
G
G
should
should
be
be
set of
set of
all
all
positive
positive
integers.
integers.
So
So
we
we
should
should
write it
write it
as
as
uh, n.
n.
So
So
and
and
the
the
uh, and the
and the
operation
operation
should
should
be
be
A
A
dot
dot
B
B
as
as
AB.
AB.
So
So
this
this
is
is
nothing
nothing
but the
but the
usual
usual
product.
product.
And
And
for
for
C,
C,
we are given shade
shade
A0
A0
to
to
A6,
A6,
where
where
uh, AI
AI
dot
dot
AJ
AJ
should
should
be
be
AI
AI
plus
plus
J
J
if
if
I
I
plus
plus
J
J
is less
is
than equals to
equals to
6,
6,
and
and
should
should
be
be
uh,
um,
uh,
uh,
AI
A I
plus
plus
J
J
uh,
uh,
mod
mod
7
7
if
if
I
I
plus
plus
J.
J
Let's put it on 7 and
and
D.
D.
G is
G is
the
the
set
set
of
of
all
all
rational
rational
numbers
numbers
with
with
odd
odd
denominators.
denominators.
So
So
you should
should
note
note
down
down
as
as
B
B
belongs to
belongs to
Q,
Q,
B
B
is
is
odd,
odd,
and the
and the
operation
operation
should
should
be
be
A,
A
I mean
and
A1
A1
by
by
B1
B1
dot
dot
A2
A2
by
by
B2
B2
should
should
be
be
their
their
addition,
addition,
the
the
usual
usual
addition of
addition of
rational
rational
numbers.
numbers.
So
So
class
class
আছে,
wise,
sorry
sorry
about
about
that.
that.
So
So
yeah,
yeah,
uh,
uh,
I
I
think you
think you
should
should
give
give
each
each
of
of
them
them 1 or 2
1 or 2 minutes
minutes
and
and
let
let
me
me
know
know
if if you
if you
have
have
done it
done it
or
or
something is
something is
creating
creating
problem.
problem.
Yeah. So
So
if you
if
are
you are
uncomfortable
uncomfortable
with
with
mod
mod
7,
7,
yeah, you
yeah, you
can
can
just
just
replace
replace
with
with
minus
minus
7.
7.
I think mod
Mod
7 is
7 is
more
more
accurate,
accurate.
but anyway.
Anyway,
And
and
if you
if you
are
are
unable to
unable to
talk, you
talk, you
can
can
raise
raise
your
your
hand
hand
so
so
that I
that I
can
can
understand
understand
if
if
something
something
is
is
wrong.
wrong.
Uh,
Uh,
is a
Age a
group.
group,
Okay.
okay.
Um,
Um,
if you
if you
could
could
tell
tell
me
me
why
why
you
you
think
think
A is a
age a
group,
group,
that
that
would
would
be
be
nice.
nice.
Sandeep.
Sandeep,
I
I
mean,
mean,
if
if
you
you
are
are
not
not
able to
able to
talk,
talk,
then it
then
is
it is
also
also
fine.
fine.
But
But
so
so
there
there
are
are
uh, four
four
group
group
axioms,
axioms,
right?
right?
That
That
is,
is,
it has
it
to be
has to be
closed
closed
under the
under the
operation.
operation.
Then it
Then it
should
should
be
be
the
the
operation
operation
should be
should be
associative.
associative.
Then it
Then it
should
should
have
have
a
a
unique
unique
identity
identity
element,
element,
and
and
uh, and
and
it
it
should
should
have an
have an
additive,
additive,
I mean, inverse
inverse
element.
element.
So
So
what
what
about
about
the
the
associativity?
associativity?
Can
Can
you
you
check
check
it?
it?
Yeah,
Yeah,
all of
all of
them are
them are
fine.
fine.
But
But
what
what
about
about
associativity?
associativity? Can
Can
anyone
anyone
else
else
tell
tell
me
me
if
if,
yeah,
yeah,
are you
are you
sure?
sure?
Okay.
Okay.
I
I
think we
think we
should
should
start
start
writing
writing
down
down
the
the
answers.
answers.
So,
So,
okay. So,
so
solution.
solution.
Now,
Now,
clearly
clearly
the
the
operation is
operation is
uh, well
well
defined,
defined,
and
and
it is
it is
also
also
closed
closed
under
under
subtraction.
subtraction.
There
There
is
is
zero
zero
and
and
there
there
is
is
negative
negative
a.
a.
So
So
these
these
things are
things are
fine.
fine.
But
But
for
for
a
A
dot
dot
b
B
dot
dot
c,
C,
we
we
have
have
a
A
minus
minus
b
B
minus
minus
c,
C,
right?
right?
That
That
is
is
a
A
minus
minus
b
B
minus c.
minus C.
And
And
for
for
sorry, a
A
dot
dot
b
B
dot
dot
c
C
should be
should
a
be A
minus
minus
b
B
minus
minus
c,
C,
right?
right?
So it
So it
should be
should be
a
A
minus
minus
b
B
plus
plus
c.
C.
So
So
you
you
see
see
that
that
when
when
c is
C is
non-zero,
non-zero,
then
then
these
these
are
are
not
not
equal,
equal,
right?
right?
So for
For
c
C
not
not
equals to
equals to
0,
0,
we
we
have
have
a
A
dot
dot
b
B
dot
dot
c
C
not
not
equals
equals
to
to
a
A
minus
minus
b,
B,
sorry,
sorry,
a
A
dot
dot
b
B
dot
dot
c,
C.
mm,
Mm,
not
not
equal.
equal.
So
So
g
G
is
is
not
not
a
a
group.
group.
Also,
Also,
here
here
a
A
minus
minus
b
B
has to
has to
be
be
a
A
minus b
minus B
has to
has
be
to be
non-zero.
non-zero.
Now
Now
let's
let's
come to
come to
the
the
question
question
b.
B,
That
that
is
is
g is
G is
natural
natural
numbers
numbers
and
and
a
A
dot
dot
b
B
is
is
ab.
AB.
But
But
you
you
can
can
see
see
that
that
it is
it is
not a
not a
group,
group,
right?
right?
Because
Because
for
for
a
A
greater
greater
than
than
1
1
from
from
n,
A,
let
let
a
A
dot
dot
b
B
equals
equals
to
to
1
1
for
for
some
some
b
B
belongs
belongs
to n,
to
right?
N, right?
Then
Then
if
if
uh,
uh,
a
A
inverse
inverse
exists,
exists,
then
then
uh,
uh,
I
I
mean
mean
b
B
should be
should be
a
A
inverse,
inverse,
right?
right?
But
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 n
N
belongs
belongs
to,
to,
I mean
I mean
n is
N
a
is a
subset of
subset of
q,
Q,
and
and
a
A
dot
dot
1 by
1
a
by A
equals to
equals to
1.
1.
So
So
as
as
q
Q
star,
star,
q
Q
star
star
means
means
q
Q
minus
minus
0
0
is a
is a
group.
group.
So
So
by
by
uniqueness
uniqueness
of
of
uh,
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 inverse,
inverse,
a
A
inverse
inverse
should be
should be
1 by
1 by
a,
A
and
and
1 by
1 by
a
A
does not belongs to Z, A and A, right? So G is not a group. I mean, these can be said easily uh, when you talk to people, but as these recordings will be uploaded to YouTube and these notes will be available on the website, so I have to write it precisely. Anyway, now what about uh, question, question C? So one thing is clear, right? That it is closed under this operation, and you can see that A0 is the identity element, right? And for any element AI, A7 minus I is inverse of AI, right? Okay, I will write all these things clearly. So clearly, G is closed under operation, and star A0 dot AI equals to A0 plus I is AI, and similarly follows from here. So A0 is identity element, and for any AI 7 minus I, it should be A7, and as I plus 7 minus I is greater than 7, so we write it as A7 minus, sorry, A7 minus 7, so A0. And it follows from this also, 7 minus 7. So so it has, not it has, every element has its own inverse. So G is a group. So one might one might ask, uh, how do they look? I mean, you will be introduced to this later. Should look like this. An example. Of course, we don't have idea if G is abelian or not, but this is at least a group. Morely, this is an abelian group. So some of you might be already familiar with all these topics and uh, basic things. Okay. Uh, I will avoid the headphone here. So wait a minute. Now is it clear? I think it should be clear now. Then notepad was taking the uh, was recording the voice, so I forgot to turn it off. Okay, so we will go to the next question. That is, G is the set of all rational numbers uh, such that the denominator B is odd. So uh, what about this?
So it is closed under this operation.
Yeah, it is closed, and also 0 is there because you can write 0 as 0 by 1, and to every element a by b minus a by b is there. So yeah, this is a group, right? uh, so left as an exercise. Answer is affirmative. Okay, so we'll go to our next question. That is, so uh, before that, we'll be knowing what is an abelian group. So because these are all like starting points of algebra 1. So if you have not been introduced to what is an abelian group, you will be later. So let me just tell you. So let be a group. G is said to be an abelian group. So this abelian name comes from a great mathematician named Abel. Uh, if for all AB belongs to G, we have A dot B equals to B dot A. So that means what? That they commute with each other. Uh, in group theory, we say this as abelian group, but when we go further, like in ring, uh, algebra, they are called as commutative objects. Or anyway, so what should be an example of this, right? Uh, Example: take Z with addition. So for any element you take n1 plus n2, it should be equals to n2 plus n1, right? Because this is simply counting of two numbers. You are just adding two numbers. N1, N2 belongs to Z. So again, so let us see which of them are abelian here. So already we know A and B are not group. And what about C? So you know that AI plus J equals to a J plus I, right? Because I plus J is nothing but index here. They are just keeping the data of an element. So AI dot AJ should be equals to AJ dot AI. So this is an abelian group, right? And again, similarly, D is an abelian group because uh, I mean, if you take Q, Z, by a similar argument, you can say that it is also abelian, and any subgroup of an abelian group is abelian. So I'm just letting you know I will be not doing the proofs here because our aim is to do exercises, but these are all standards and very elementary. We will be getting used to it as you do more exercises and do more
Sir,
studies. Yeah,
sir, you have written that third group is isomorphic to Z6,
yeah. I mean, not isomorphic, just giving you a sense
but
of that.
G has 7 elements.
Z6 or also have. Oh, sorry, what have I done? Sorry. Yeah, here 6 equals to 0, so that would be just 0, 1, 2, 3, 4, 5. Yeah, sorry. Thank you for uh, the correction. Yeah. So I mean, I think you are right. It can be, you can say that they are isomorphic in a if you do the proper mapping between them. But as you are not introduced in this course what is an isomorphism yet, so we may let discuss this later. Okay, okay. So we'll be going to our next question. Anyway, thank you for this correction. So we'll be going to our next problem, that is, so prove that if G is an abelian group, then for all AB belongs to G and all integers n belongs to Z, we have A dot B for n equals to A n dot B n. So this is just switching the elements in a sequence of elements. The just I think there is nothing to be, nothing serious here. Just I will just write it down. So root to the power n should be a dot b dot a dot b a dot b up to n times, right? Now, uh, I mean, you just take this part and fix this part, and using associativity uh, in a consecutive way, you can just forget all the brackets and write it down as this dot b a dot b. Now, as the group is abelian, you can just take this part and write it as this b. Let a dot b to a dot b. Again, you can just uh, change this part, write it as a dot b dot a dot b dot b a dot b. Again, you can change this part. It should be a dot a. So you are getting a sense how you are approaching this problem. Dot b, and again now you can just take whole bunch of this element as a single element and change this to other part. So this way we'll be getting that a dot a to a and b dot b to b. So both will be n times n times, and it should be a to the power n, b to the power n. So you see that what we have been learning from our childhood, that if you are given two integers and their powers, it should be like 2 dot 3 square should be 2 squared 3 square. So when you learn this is in a more generalized way, then you see that this is not always the case. The things we have taken for granted in mathematics till now are not always uh, those, because there are certain groups, like in you are already familiar with matrix, right? So if you take 2 cross 2 matrix, and there are several examples that you can try, that if you take A as a matrix and B as a matrix, you will notice that A dot B might not be equal to B dot A. And it is easy to construct an example, but I'm sure you can find it yourself. Okay. Now we'll be approaching a similar problem, but little different. If G is a group such that A dot B square equals to A square dot B square, uh, for all AB belongs to G, so that G must be abelian. Now this is fun, right? Because uh, you already have we all know that the converse is true, right? When G is abelian, this is true for all n. So for square, this is also true. But the thing is that if this result is true, we have to prove that G must be abelian. Now I'll give you some time to think about this, and those who already know can can give me a hint to how to approach this. Know that every element has an inverse, and that is unique inverse. So maybe you should use that. এ তোরা একটু আস্তে কথা বলিস, একটু আস্তে। So can anyone tell me how to do it? Yeah, the cancellation law should be applied. Okay, the the one line is enough for the solution that what you just said, but for the sake of completeness, we will be writing the proof. Okay, so for all a b of g, we have a dot b square equals to a square dot b square, right? So it can be written as a dot b dot e dot b, a dot a, b dot b. Now it can be written as a inverse a b, a b, a inverse of a b, a b. So this should be e, this should be e, this should be e. So we ignore them and it becomes b, a dot b equals to a b b. Now again you apply right cancellation law, that is b dot a dot b dot b inverse a dot b dot b dot b inverse, and it becomes b dot a equals to a dot b. So we are done, right? A and b was arbitrary, so this is complete. Now in the book there are two more problems following this, but uh, we should go to the permutation group because it was the first lecture. So yeah, let us do some uh, those kind of problems. So you already know that Asian is the permutation group of n letters or n numbers or n object. So in S3, give an example of two elements x comma y such that what we have just did for abelian groups. So we have an example of a non-abelian group, right? So can anyone write down uh, the x and y from S3? Okay. Uh, so first, let us write about the elements of S3. So there are two generators in S3, right? Uh, Solution. So S3 should look like this. That is E psi psi square uh, phi psi dot phi and phi dot psi. Now, for those wondering what these elements are, it should be second bracket. 1, 2, 3, comma also. 1, 2, 3, and phi can be any one of them. 1, 3 or 1, 2 like that. So yeah, with psi cube equals to E, phi square equals to E, and uh, phi dot psi I dot phi equals to psi minus phi. Now, now coming back to our notations, choose x equals to psi and y equals to phi. Then you see that x dot y square should be psi of phi square equals to psi of phi dot psi of phi, which is nothing but psi dot phi psi phi, that is psi of psi inverse and E. Now x square dot y square should be psi square dot phi square, and we know that phi square is E, so it should be psi square dot E, so psi square. And we know that psi cube is E, so this is not equals to E, so we are done. So actually what we show just that if you take two generators, so any two generators, then you can show this result. Okay, now we'll be sticking into this S3 again, question 5. In S3, show that there are four elements satisfying x square equals to E and three elements satisfying y cube equals to E. I think this is relatively easier as we have discussed these things. Maybe you should take help from those and try yourself and write it in Uh, okay, Ramanathan. For 1, 2, and 1, 3, are you sure they would be true? Maybe I did not check, but seems like they are conjugate to each other because you know that any two like cycles of same length are conjugate to each other. So you may check that if they do not um, or do follow these things. Anyway, is this angle fine or this angle fine? I think this angle is better. Okay, so again we take S3 as uh, E psi square phi dot psi and psi dot phi. Now for x, like for the elements whose square is identity, one thing is there is uh, E square equals to E. Now phi square equals to E. If you take phi dot psi, should be phi psi dot phi dot psi. Now phi psi phi psi, it should be psi inverse psi and e. And for psi dot phi square, it should be psi dot phi dot psi dot phi. So again, we just take phi dot psi dot phi psi psi inverse to e. So there are four elements, right? And for the cube thing, you have cube equals to e, and again psi cube equals to e. Now you have psi square cube equals to psi this and so this cube square psi square. So these are just routine procedures and to solidify your uh, group theoretical techniques that that will be useful in your uh, competitive exams, intern states, tests, and interviews, everything, and overall your math skills. Now, should go to our next problem. Should be problem 6. Now, this one is interesting. If G is a finite group, so by finite group I mean that a group with finite number of elements that we just talked about earlier. Uh, that is Z7 or something. Yeah, yeah. C. So, like there are a big class of examples apart from your Z, Q, uh, like real numbers, complex numbers. Anyway, uh, show that there exists a positive integer n such that such that a to the power n equals to e for all a belongs to G. So this is important, right? Because what we are claiming is that there should be an integer, should be positive integer. I mean, if there is a positive integer, then it is also true for negative integer also, because you just multiply, sorry, you just multiply it by a to the power minus n at a minus n, so it should be a to the power minus n should be. So in your now this n is being positive, so it has a lower bound, right? Because this n starts from 1, so there should be a minimum positive integer which satisfies this. Now it is quite interesting to know that uh, uh, I mean, there is a notion called cyclic group where this n is exactly the order of the finite group. That means the number of elements in the group. But if the group is not cyclic, that means it is not generated by a single element, then you should know that this capital N can be smaller than the order of group also. For example, if you take Z2 cross Z2, here every element has order by order I mean the least positive integer such that e to the power n equals to e. Every element here has order 2, but yet the order of the group is 4. Those will come later. So if any one of you can give me a hint how to do this. বলো, আমি ভিডিও অফ করে দিয়েছি। হ্যাঁ, আছে ৬-৭ জন আছে। এগুলো প্র্যাকটিস হচ্ছে। কোথায় এটা? এসএসসি? এসএসসি মানে আমাদের? বাবা, আলাদাই তো। কবে আছে কবে? কবে আছে কবে? ও ডেট দিয়ে দিয়েছে। তোমার বিএড আছে? বিএড আছে? So anyway, we'll be doing this. Okay. Now, since G is finite, uh, we assume the cardinality of G is n. that is J consists of elements small g1, small g2 up to small gn for some positive integer n. Now for some small gi of G, consider the sequence gi, gi square, gi cube. I mean, consider this as an ongoing sequence as uh, the the upper index is getting larger. Now, since G is closed and G is closed under binary operation and G is finite, so there must be repetition, right? Must be a repetition in the sequence, or else will be like going in infinite time, so we'll be getting infinite elements, which is contradict the fact that G is finite. So that is G uh, I of J Gi of K for some integers J and K with J greater than K, obviously positive integers plus few. This means Gi of Gj minus K. That is, if you take inverses of Gik on both sides and multiply them, it should be E, where E is identity element and J minus K is greater than 0. So, so what I'm trying to say is that that means what? That is J minus K is greater than equals to 1. So this means what that either Gi equals to identity or uh, or or some power of Gi is identity, right? So let's take J minus K as A9. Now, if Gi is not equals to identity, then Ni is greater than 1. So, for every I, we have Ni greater than equals to 1. I should write it like this. For every I such that Gi not equals to E. So, taking N to be mean of Ni, I, we are done, right? See, these proofs can be written in a much more compact form, but I'm writing as explicitly as I can so that when you again look at these notes, you can understand in a in the most trivial way. Okay. Now we'll be doing some interesting uh, numerical problems. Not numerical, but these are not rigorous as the last proof went on. Okay. Uh, if the group G has three elements, so that it must be abelian. For B, check the same if G has 4 and 5 elements respectively. So you can ignore the 5 part because it will be little rigorous and difficult to do in a class. Maybe you can uh, try it as an exercise. And also when we'll be introduced to this, if order of a group is prime, then it is cyclic, and cyclic means abelian. Those will be coming later. But anyway, we should for now check these two cases. So first one is just a proof, and second one we have to check. You can tell me if you are done. I just want you to try this also because so far this meeting has been pretty much one way. So it would be interesting if you guys can engage in this class also. Okay, so solution for A, let G should be A, B, E, right? So one thing is clear that A not equals to B and A not equals to identity and B not equals to identity, right? Because if this is the case, then it would contradict the fact that G has order 3. Now, what about A dot B? Because it is closed under operation, right? So it has to be the, one of these. So if A, that would imply that B equals to E. But this is a contradiction. If A dot B equals to B, this should imply A equals to, which is again a contradiction. So only way is that then A dot B equals to E. So again similarly you can check the other way. I mean this case. So the something. Okay, let me restart the app. I think the app has crashed. Then this is the only way. So then G is abelian. Now for the second part, this is quite rigorous. So okay, let us do this. Let G be a group of order 4 and let A dot B belongs to G. We do not assume if A and B are identity or anything. So there is case 1, either A or B equals to E. Then clearly we have A dot B should be let B equals to E. Without loss of generality, I mean we can also take A equals to E. So it would be this E dot A, B dot A, yeah, because identity commutes with every element. Now we come to case 2. that is A not equals to E and B not equals to E. And clearly, like the previous case, A dot B not equals to A and A dot B not equals to B. But now G has four elements, right? So let C belongs to G be the fourth element. So here, so either A dot B equals to E, then A dot B equals to B dot A, as in the previous case, or A dot B equals to C, right? Now, in this case, again, B dot A is not equals to A and B dot A is not equals to B. So, either B dot A equals to E or B dot A not equals to E. So, for the first case, done. And in the second case, there is only one option, right? See that this would imply this, and this would imply it. So the proof seems rigorous only when we have to be notationally correct. So that is why there are tools and standard theorems that will be introduced later, so that you don't have to do these things in this way. Like later you will know that if order of G is p square, that is prime square, then G is abelian. Now here it was 4, right? So that is 2 square. That means G is always abelian. So these are all standard theorems that will be introduced to you later, so that you don't have to do these things rigorously. But I am doing this so that you know how boring it is. Anyway, okay. So again, uh, let us do another problem. Wait. So this one is interesting. Uh, show that if every element of the group G is its own inverse, then G is abelian. I mean, this should be easy. You should try this, and I'm going to take a break for 2-3 minutes, and I will come back. And let me know in the message section that if you are done, or you can write your solution also. So, anyone? Okay, okay, let us do this. Uh, we prove this result by contradiction. That means uh, we assume that negation and show that then G is not available. Uh, so yeah, let's assume uh, there is no element X satisfying x square equals to E except x equals to E. That is, if G belongs to G with G not equals to identity, then G square is not identity. That is, G is not its own inverse, right? Oh no, we don't need to do this uh, this way. Just just simply use another trick that um, yeah. So let AB belongs to G with A equals to A inverse and B equals to B inverse. Then A dot B equals to, I mean, not then. Now, this is also true as A dot B equals to G, right? Now, this means what? This means it should be B inverse dot A inverse, right? This is because, I mean, this is simply you take this like this A dot B dot A dot B inverse should be E, right? And you just take left cancellation uh, two consecutive times and you'll see that it should be B inverse dot A inverse. Anyway, so yeah, it should be B dot A. Then we are done. Yeah. Uh, yeah. Now go to the next problem and we'll be seeing that. Yeah, you are right. Chaitrali, yeah. Uh, hmm. So now you all are getting the sense of the cancellation, importance of the cancellation law in group theory and in a finite field theory and finite algebra where the number theorist and the research is active, there this cancellation law is very much important. Uh, okay, so let us do another problem. Yeah, this would be interesting. Suppose a finite set G is closed under an associative product and that both right and left cancellation laws hold. Prove that G must be a group. Okay, this is little fundamental to prove the claim I just made earlier. So for the sake of fair chance, I will give you 1 to 2 minutes if you can give me any insight about this. Any other way I will prove this. So first of all, notice that G is finite and it is closed under product and also it is associative. So two properties are already done, and using associativity you have to see if it has a unique identity element and uh, of course every element has an inverse. Well, okay, the proof will be rigorous but it will be interesting, so I request you to follow this because yeah, since the finiteness of the group is important, since G is finite, let us assume that G equals to G1 Gn for some n. Now let A belongs to G. A can be any of Gi's. Uh, Consider the set S equals to A dot G1, A dot G2 up to A dot G1. Now we already told that cancellation laws hold. So if AGI equals to AGJ for some I comma j, then GI equals to GJ, I not equals to. Contradiction. So cardinality of S equals to cardinality of G. That means uh, this implies S equals to G, right? As S is a subset of G. Therefore, A belongs to S, right? But A belongs to S because originally we took A from G and we have shown that S equals to G. So we have A equals to A belongs to S. But this means what that A equals to A dot GK for some GK belongs to G. So we claim that GK is the right identity. That means if you product uh, to the left of this element, product any element to the left of this element, then you will be getting the other element. Now again consider S prime like S as G1 dot A, G2 dot A up to Gn dot A. So then uh, S dot should be G, and again S dash should be equals to G, and Gj dot A should be equals to A for some J. Okay, just do it another way. Let why did we get a contradiction here? Okay, Fair question. So what we have shown that every element of this set are distinct, right? So and there are n elements here. So cardinality of S and G are same, right? So I think up to this part there is no question. Is it all right? Okay. So now we already have that S contained in G, right? Because A belongs to G and all the Gi belongs to G. So A dot Gi all belongs to G. So S belongs to G. Now what I have done here, used here is the pigeonhole principle, right? That if we take a subset from a finite set and if the cardinality of both the sets are equal, then they are equal, right? I think you are asking about this contradiction, right? Okay. So if yeah, by contradiction I simply meant that uh, I mean, so it is better if I don't write contradiction. Just I'm trying to say is that if this happens, then this happens. But we already here we have taken G to be this where all of the elements are distinct. So so we have A dot Gy to A dot Gj for every ij. I think this is fair. Yeah. I should not write contradiction as I am not claiming anything. Thank you for correcting me. Yeah. So I think the rest of the proof is clear, right? Okay. Yeah. Now let us assume that uh, let x belongs to G. Then uh, then x belongs to S dash. Therefore, x equals to Gi dot A for some Gi dot G. Now x dot Gk equals to Gi dot A dot Gk equals to Gi dot A dot Gk is nothing but Gi dot A and which is again nothing but x. So thus x was arbitrary. Thus x dot Gk equals to x for every x belongs to G. So uh, our claim is true. So Gk is sorry. So Gk is right identity. Now since uh, Gk is the I mean since Gk belongs to G, therefore GK belongs to S. So as S is this set, so GK equals to A dot GL for some GL belongs to G. But this means what? That this means GL is the right inverse of A with respect to the right identity GK, and A is arbitrary. A belongs to G is arbitrary. So the right inverse exists for uh, each element, and it is an exercise that if the right identity and right inverse exists for each element, then G is a group. So the last part, I'm simply leaving it because uh, because you should try this uh, in your uh, in your free time, and let me know that if you have done it. My email is mail ID, so you should send me this if you have done it. Okay, so maybe we should do another problem, and then call it a night. And okay, so following this exercise 9, so what we have seen is that for finite groups is this is true. Now uh, prove that in exercise 9, infinite examples exist satisfying the conditions which are not groups. So think for 2 or 3 minutes and let me know if you come with an example. So what we have actually seen in this class or in this tutorial session that uh, the the problems which seems trivial when you do them rigorously without having much tools in your hand, they are quite intriguing and rigorous. So it is important to learn tools to solve problems in group theory, which will be taught by your instructor in coming classes. Anyway, uh, okay, try to think this, and we'll conclude this session. Okay, okay. We define AN as IN, where your I is coming from N and N is greater than 1. N is a positive integer and N is greater than 1. So AN with usual binary operation uh, that is multiplication satisfies all the conditions given in exercise 9, but they are not groups as universes to each elements of are not there in AN. So you can check this by yourself. Yeah, integers under multiplication. I have taken positive integers under multiplication, and similarly you can take negative integers under multiplication also. But we are just forming a class of examples. Just that. I think this is clear, right? I mean, you can put a dot here. It is just a lazy writing. Yeah. Okay. So if you have any more doubt, you can ask me, or else we'll just conclude this class. Okay. Okay. So thank you everyone. We'll meet next Tuesday. Till then, do study well. Okay. Good night.